Student, I think it's better to review this previous slide because in the last time somehow I was in hurry. Okay, so I should repeat this. So lecture 9 is about the time domain performance of buck converter, voltage mode controlled buck converter, and through the design example, we went through all the details about the structure of voltage feedback compensation and how to select the parameters for the voltage feedback compensation, and we obtained good frequency response characteristics. Okay? Frequency domain performance, but that is related with time domain performance. So relationship is this one. Okay? So we have two important transient response of output voltage. One is step load response. So this is the response of output voltage in the case of the step change in the load current or load resistance. And the other one is transient response of output voltage due to the step change in the input voltage. The student may wonder why we are concerning about the step change. Okay, there are many different kind of change, but this can be used as the barometer of the transient performance of the converter in general. If converter has good transient response, step load transient response, this converter is well designed and it will generate good response for any type of transient response. Okay, so this can be used as the measure of determining the goodness of your design. Okay? So we are using this, okay? And there are many cases this actually occurs. Suppose your converter is driving the digital load, okay? Then digital load will switching every time. That is very similar, the step load change. Okay? Sometimes the input voltage will be changed in step manner for some special cases. So we are interested in these two transient responses, and they can be used as the measure of judging the goodness of your design or transient performance of your converter in general. This is the equation you're going to use. This is our voltage, and this is the S-domain differentiation of step change in the load current, and magnitude of step change is I step. Because of this step function, this is the S-domain expression of that disturbance source. Okay, simply S is coming in the denominator, and this output impedance is a closed loop transfer function from load current to output voltage. So this is the disturbance source, and this is the transfer function. Then multiplication of them will become the S-domain expression of output impedance. Then you take inverse Laplace transformation of that, then you will get the output impedance. No. Output voltage waveforms in time domain expression or waveforms. If you perform the simulation, you get the waveforms, simulate waveforms, and actually you can get the expression in time domain if you take the Laplace transformation, okay, manually. Same is true for this input response of our voltage. Here everything remains the same, but this is the S-domain expression of input voltage change of the magnitude V step, and this is audio susceptibility, which is a closed loop transfer function from input voltage to output voltage. Okay, so this is the background. Background is very simple. Okay, so first we take a look at the step input response. Okay, and in particular, you want to know the relationship between compensation zero and transient response speed. Okay, so this is the compensation zero. So you need this integrator to regulate output voltage in constant value. For DC regulation, you need this. Later on, you will find out this omega G1 is determining the speed of step input transient response of our voltage. This omega naught is coming from the power stage configuration. This is power stage double pole, right? And you will learn this omega G2 is determining the speed of step load response. And this omega c is determining the phase margin of this converter. Okay, and omega p1, they cancel with this, and it maintains this -1 slope for the wider frequency range. And this omega p2 is required to attenuate the high frequency noise or switching ripple. So they have a good reason, okay, to appear here. All right. So all of them are necessary. Okay. If you take out something, then you are in trouble. Okay. And again, this omega G1 is coming before this omega naught, and omega G2 is coming after this omega naught. Otherwise, the converter becomes conditionally stable, which is worse than unstable system. Okay, and this should be before this to have sufficient phase margin here. Okay, so this is the optimal structure for the buck converter, and this is the result of asymptotic analysis. You are using this. Okay, this is another approximation. This is a new definition. So before this frequency, where the magnitude of the loop gain is larger than unity, okay, it really doesn't matter how much larger than, just small number is okay. Then we are using this, and the other side at high frequencies we are using this. Okay, so you know the rule of this, constructing this. Right? This is open loop transfer function, and this is a loop gain. But then after this loop gain crossover frequency omega c, you take this, and before this you take the subtraction rule. Okay, or you know the relationship between this slope. Okay, so you need some practice. Okay, then this is almost automatic. If you see this, then you can plot this immediately with some practice. Right? Maybe it will be difficult for the first time you sketch this, but maybe 5 times practice will make you expert on this. Okay? Then from this plot, you extract the expression of this closed loop transfer function audio susceptibility. Initially, we have this differentiation, so KAS, and there is a pole, another pole, and the 0 is coming here. So there are 3 poles, 1 0. Okay, and this is a relationship. Omega G1 is coming first, and this is the second. This one is last, and there is another one, omega ESR, is coming at the end, and maybe omega P2 is here. Okay, all right. But they are widely separated in general, not very widely, not like 10 times or 20 times, maybe 3 times, 5 times is wide enough for this case. Okay, so we have this relationship. Then next step is think about this. Okay, so this is the output response in time domain, and this is output response in frequency domain, S domain, and there is inverse Laplace transformation operation. And this is what? This is the S domain expression of step input change, and this is the audio susceptibility. So you have S here, but audio susceptibility has S in the numerator. So here is S, and here is another S here. They cancel, and they cancel out, and you have this. Okay, so you have 3 terms here. Think about the partial fraction expansion. Then you have some term coming from this part, this part, this part. So there are 3 terms, exponential terms. Each of this fraction factor will generate the exponential function of this type. Okay, so one is this one, this form, and the other one is this form, and another one is this form. Because we have this relationship, this omega J1 is much smaller than the others. Then this will be the what? It has the name dominant. Dominant pole. This thing is dominating the speed of response. Okay, so each of this fraction factor will generate this one, this one, this one, and this guy decays very fast, and this guy is very slow. So the time constant of this one, if you think about the sum of three terms, time constant is determined by the slowest term. Okay. So previous time I made a mistake. So this tau is the time constant is 1 over omega g1. This one was wrong. This one is mistake. Okay. So time constant of this waveform tau is 1 divided by omega g1. So this is slow. Okay. So 5 time percent bound settling time is the time period required. The transient response settles in 5% of its final value and stays within the final value. Okay, it goes into final 5% of final value, and it never comes out of that region. It stays there. That is the definition of this 5% bound settling time is given by 3 times time constant, which is this one. Okay, so for the fast response, you should increase this, right? So, but our design rule is this one. So omega g1 is some number between 60 to 80% of this power double frequency. If this guy is beyond this omega naught, the system becomes conditionally stable. It is absolutely unacceptable. Okay, so you need some margin. So probably this is a good number. Okay. Considering some margin or uncertainty on something, tolerance of component or the miscalculation of the something, so this is a good number. So we are using this number somewhere here. Okay. So this is the story of the previous lecture. Okay. Okay. All right. I have one example actually. I have 2 plot, but that is one example. You take a look at this. This audio susceptibility has some corner, but in reality, this corner frequency is not far aparted. Then it becomes this continuous curve, something like this. Okay. So the result is this. This is the simulation result. Okay. So this black curve is the original design we went through in previous lecture. This is the normal design or optimal design. And I intentionally modified to move this omega g1 to lower frequency while maintaining this peak value remain the same as the previous case. Okay, so you can do it. Okay, if you know the design procedure, then you can adjust everything. Actually, you can program this by changing location of the zeros, compensation zeros. So everything is controllable, predictable, and even programmable. Okay? You can program this. Right? So I did this, and I maintained this peak value the same, and I checked the step input response of original one. This black curve is this one. Okay? And this first time is this one, because I said the 5% bound response time is 3 times this is what? This is 1 over this number is time constant. So this one is the theoretical prediction. And if you take a look at this is very similar to that. I don't know, 5%. Maybe somewhere here. Okay. So this is original design, and omega G1 was here. Okay. And with due modified Volts design, this is shift this by 3 times. Okay, so this is Ts prime is this one, and this is the same step input response, which is much slower than previous case. Right? So maybe this is 5%. I don't. All right. So with this, the settling time is calculated this, predicted as this, and actual simulation shows much smaller, much slower response, and this settling time matches with the analytical calculation. Okay, and this peak value and the peak value is proportional to peak value of this audio susceptibility. Right? So this peak value and this peak value is about the same. there is an analytical reason of this, okay? You cannot expect just this is the same, then this will be the same. Okay, nothing like that. There is a good reason for that. And later on, we'll discuss that in next section, which deals with the current mode control. This peak value is proportional to audio susceptibility magnitude maximum. Okay, so this is the same, proportional to this one. So they remained about the same, this value and this value, but this is faster, much faster. This is the optimal response. Okay, but this is a little slow. This one is a little slow. Okay, I'll explain that later. All right. Next one is output impedance analysis. This output impedance is related with step load response. So I'm using this assumption to simplify our analysis. So this one is okay. This is the open loop load current to output transfer function. But we assume this omega G1 is located here. Right? This is assumption. We'll check out this assumption later, whether this assumption is valid or not. Okay. Another assumption is crossover frequency is same as the omega ESR0. This is the second assumption. So we are using two assumptions simply just to simplify the discussions and explanation. So they are coincide with at the same frequency, not this one, okay. Loop gain crossover frequency matches with omega ESR, and the first zero, omega G1, is the location is the same as the low frequency zero at this load current to output transfer function, and you do same thing, okay? This asymptotic analysis. So after this, you follow this. This is open loop. It's the same, and before this, you use the subtraction rule, okay? Then everything is simplified. So they had the constant +1 slope up to this point, and later becomes this horizontal line, and this high frequency value of this is 20. You know this, okay? I explained this at least 2 times, okay? All right, oh boy. Okay? So then this is very simple, okay? So we are using this relationship, asymptotic analysis relationship, and then this becomes very simple, all right? So then we can do, here in the previous case, you don't need to take this inverse Laplace transformation to predict the detailed waveform of this. That is unnecessary, okay? It's very complicated, but it's not worth it, okay? You can do it if you want, okay? But that is not important. But this one is very simple, so this one is important, okay? Then this asymptotic product of output impedance is copied here. So this is the omega G2. This frequency was this omega G2 is appearing here, okay? And this becomes what? This becomes low frequency dominant pole, okay? Previously low frequency dominant pole of audio susceptibility was omega G1, which is much lower than omega G2, okay? This means this step load response is inherently much faster than step impulse response because of the difference in the compensation zeros. Okay? That is obvious from this analytical analysis. And you extend this line segment, and it crosses 0 dB at omega m. That is assumption. Then equation of this is this GOS is S is differentiation, and in the denominator omega m is here. Then when you replace S with omega m, this becomes 1. That is the 0 dB line. Okay, and you have this pole here, omega G2. Okay, this is low frequency pole or only one pole here. Okay, only one pole has the system is first order system. So transient response will show very similar to the first order response of linear time invariant system. Okay, just to calculate this, the maximum value of this magnitude of output impedance, we know this. You already know this. This is 20 log RC. Okay, but for this, you do this. Okay, so at high, this is the high frequency asymptote. Is also the maximum peak value of output impedance. Then you replace this S with this infinity and take the coefficient of them. Then peak value is this one, omega G2 divided by omega M. Okay. Then this should be the same as this because of this graphical construction. This is one thing. And another thing is, another way of doing this is just to consider this one. Up to this frequency, you are not seeing this. You are seeing just this line segment and evaluate at that frequency. Evaluate magnitude of this one, evaluate at that frequency, S equals J omega M. Magnitude of that is, omega G2, right? We are talking about this frequency. Omega G2 is omega G2 divided by omega G1, okay? We need 20 log. Okay, let me. Okay, this should be this one. All right. Okay. So we know everything about the output impedance, and we use this. Okay. So this is the expression of output impedance, and this is the S-domain expression of I step. Then they cancel this S gone, and you can easily, automatically, you can write down this equation. This is the time domain equation of step. Load change response of the output voltage. Okay, this is extremely simple. Right? Then the initial value is the maximum value of this. Okay, initially t is 0, then this becomes 1. So maximum value is this one. Evaluate at t equals 0. So I step times this, and this becomes 1 unity. So it becomes this, but this one is what? This is the maximum value of output. Funny. Okay, so you know the maximum value of this in log scale. Okay, so you convert that log scale maximum value into this linear scale. So this is the maximum value in linear scale. It should be the same. Okay, so this is the same, and this is actually should be omega G2 divided by omega M should be RC. Okay, because you know everything. This is 20 log RC, 20 log this one, and this is the log scale, and it's changed to linear scale like this. Okay, and 5% settling time. 5% bound settling time is 3 times this tau. Okay, and this is a plot of this one. This one. Okay, so initially it goes to this peak value, which is this. Okay, and which is I step times omega G2 divided by omega G1. I step omega G2 divided by omega M is I step RC. Okay, so this is the transient response of our voltage. So but this is the converter. So you have some switching ripple. So actually waveform is something like this. Okay, so this is the first order system response. It has only one exponentially decaying constant, and this is the maximum value. So maximum value, maximum deviation in the output voltage occurs at the instant of step change. So it's called the initial jump. So for this case, there is an initial jump. You cannot avoid this. this is initial jump, okay. How do you minimize this? This is fixed. Then you should minimize ESR of this capacitor, okay. So using small ESR capacitor is very important in this case, okay. You cannot reduce this any further than this, right? This is the absolute minimum you can obtain, all right. Okay, let me give you the detailed example. This is the output impedance. We went through this before. So this is the loop gain. This is the open loop. Load current to output transfer function. This is the closed loop output transfer function. So this is the loop gain crossover frequency. So after this, it follows this open loop, load current to output transfer function. And below this frequency, we have this substitution rule. So area of this and the area of this should be the same. They look different in shape, but area is the same. That's the way we construct this, okay? That's the result of asymptotic analysis. So we have this, okay? So in here, okay, we know this, we designed this, the omega G2 is this one, and this peak value is, this is 20 log RC. There's 20 log. It was point something like this. It's minus 26 dB. Okay, I think this is okay. Okay, this is correct. Okay, so this is the maximum. The final value is slightly lower than this. We assume that this is the horizontal line. Then this final value is this one. Okay, so GO peak value is actually this one, 20 log RC. All right, we are ignoring the small deviation here. Okay, then how about the previous assumption? We used two assumptions. One is this one, omega G1, and omega X is the same. So we compared the real with the real data. So it has this one. So they are similar but not exact. Okay, maybe 3 times is okay. All right, so it's slightly different. Okay. 3 times, 2 times, something like that. And this one, omega C and omega ESR is very similar. Okay, so it really happens. This is valid assumption in almost all practical case. Okay, even though they are different, the analysis based on this assumption is very accurate. If there are some difference, the impact of difference is negligible. So still you can use this approximation, right? So what I'm trying to say is this assumption does not require to be exactly met. Okay, still in general is okay. All right. So with that, I sketched. This is the step load change, and this is simulation result, time domain simulation result of this out voltage. Okay, so this is the 4 volt, right? If this is the linear time invariant system, it should be 0. But this is the DC to DC converter. So we have this bias, and there's a ripple, output ripple, and this jumps, okay? And the magnitude of jump is this one. This initial jump, this is 0.2 volt. So final value, by adding this, the maximum value is expected as 4.2 volt. Okay, it is very similar to the almost exactly similar with this computer generated plot. All right. So when doing this, you should take the average of this because they are just switching ripple. All right, and the time constant of this one, and then this settling time is calculated as this one, and this is very similar to prediction. Okay. Okay. So this is the conclusion of this lecture dealing with the time domain performance and the frequency domain performance. And from this result, we know that although this performance criteria, okay, settling time and the maximum overshoot can be predicted, and even programmed by adjusting everything, okay? Adjusting the compensation zero, location of the compensation zero, this time, this settling time can be programmed, okay? So we use the asymptotic analysis method. Using asymptotic analysis method, you can predict all the performance criteria of your converter in frequency domain and time domain because they are closely related. That is very important. And the more important fact is, theoretically, you cannot do this. All the theory you have been using up to this time is valid only linear time invariant system. But you are applying this and you are getting good result, very good result. Why is that? We developed the small signal model. Okay? Because of the small signal model, this is all the previous analysis technique intended only for the linear time invariant system. All of them can be applied to these PWM converters to predict the performance, stability, time domain performance, frequency domain performance, transient response. All the information is predictable from the small signal model analysis using asymptotic analysis method. Okay, that is the final message of this lecture or this topic. Okay, so you should appreciate the presence of the small signal model. Right? Otherwise, you cannot do anything. You can do something, but it's not systematic. Okay, you can duplicate this result, right? By chance, you can get something good, but you know why your converter is good. Okay.